We've just spent several lectures talking about the electronic band structures of solids. And now that we have a working knowledge of band structure, we are in a position to start talking about the properties of materials. And the two properties that probably follow most directly from the band structure are the optical properties and the electrical conductivity. In the next several lectures, we're going to look at the latter, electrical conductivity. If we want to talk about electrical properties, the logical starting point is Ohm's law, which written in this form says that the current that flows through a conductor is equal to the voltage drop over the resistance of that object. Now, Ohm's law is all well and good, but all of the quantities here are extrinsic quantities. So ultimately, the material property we're interested in has to do with the resistance. But if you think about it, the resistance is going to depend on the dimensions of our sample. So if I'm measuring the resistance of a copper wire, as the wire gets longer, the resistance is going to go up. And as the cross-sectional area of the wire gets smaller, the resistance is also going to go up. As someone who is interested in understanding and designing materials, we need to be working with intrinsic properties. Such properties do exist. Instead of the current, we could talk about the current density, which is the current divided by the cross-sectional area. Instead of the voltage drop, we could be talking about the electric field intensity, which is the voltage drop divided by the length over which that drop occurs. And instead of resistance, we could be talking about the resistivity, rho, which is equal to the resistance times the cross-sectional area divided by the length. Okay, now let's take Ohm's law, the extrinsic form of it, and now let's recast it into an intrinsic form. So we can start with I equals V over R, and now let's plug in all of those intrinsic properties. So instead of current, we're going to have the current density times the area. Instead of the voltage drop, we're going to have the electric field intensity times the length. And instead of resistance, we're going to have resistivity times length divided by area, right? So each of those substitutions I just got from the formulas on the previous slide. Now when you do this, you're going to first of all see that the lengths cancel, and then notice that we have cross-sectional area on either side of the equation, so the areas cancel. And we're left with this relationship. J, the current density, is equal to the electric field intensity E divided by the resistivity. Now, another quantity that we will encounter, and we're going to talk about at length, is the conductivity, sigma. Now, conductivity is just 1 over the resistivity. We can also see that in the units. The units of resistivity are ohms times meters, and the units of conductivity then are 1 over ohms times meters. Well, there's a name for the unit 1 over ohms, and that name is Siemens. It's the symbol S. So the units of conductivity are either per ohm meter or Siemens per meter. Okay, so now that we have this intrinsic definition of the resistivity or conductivity of a material, let's take a look at the kinds of values that we see in materials. So the first thing I'd like to say is that as a property, conductivity spans an immense range. So you can see here we're spanning 28 orders of magnitude from the very best metals to the most insulating insulators. And not many properties actually span that kind of a range. We can see that the metals are in the range where the conductivity is high, as you would expect, anywhere from about 10 to the 8th Siemens per meter to 10 to the 4th Siemens per meter. At the other end of the spectrum, we have the insulators, which span quite a wide range of insulating behavior. And then in the intermediate region, we find the semiconductors. Let's look at some selected materials. Okay, so this is a table out of our textbook. And here we've got some materials that are well known for their electrical conductivity. Over here in the upper left, We've got some of the elemental metals that have the highest conductivity and are actually used often as conductors. Silver and copper, which have conductivities that are on the order of 6 times 10 to the 7th Siemens per meter. As it turns out, silver is the most conducting element at room temperature. Aluminum is not too far behind, and then we have a mixture of metals. We encounter rhenium trioxide, which we talked about a couple lectures back, and we see that it has quite a high conductivity. And then we find some other oxides. We find here's a nitride, niobium nitride. So what do we see when we look at this table? Here are a couple of questions that I have for you. What is it that makes silver so much more conductive than metals like titanium or lanthanum, right? It's over an order of magnitude more conducting. What is it that makes some oxides like rhenium trioxide and strontium molybdenum oxide so highly conducting, whereas other oxides like SiO2, aluminum oxide, and nickel oxide are in fact highly insulating? You might say, I know something here. In SiO2, in aluminum oxide, all of the electrons are tied up in covalent bonds. And, we're not going to have any partially filled orbitals or partially filled bands. And that's true, whereas that's not the case in things like titanium oxide or niobium nitride or rhenium trioxide. But then what about nickel oxide? Takes the rock salt structure. Nickel 2 plus has a D8 configuration. It's got partially filled d orbitals. Titanium oxide also takes the rock salt structure. This is titanium 2 plus, so we have 2 electrons in the d orbitals. And yet, there's 13 orders of magnitude difference in their conductivity. What's the explanation for that? We've got semiconductors on here, silicon and germanium. And if you look at the intrinsic conductivity of something like silicon, you would see it's not very conducting. But there's a whole industry, a hugely important industry that's based on the conductivity of silicon. So how do we understand the conductivity of semiconductors? And then we have organics, like Teflon, which not surprisingly is a terrible conductor of electricity. But then what about doped polyacetylene? It's got a pretty appreciable conductivity, in fact, not that far behind some of the metals. So how do we get organic systems? How do we get polymers and organic molecules to conduct electricity? So those are some of the questions that we want to answer by the time we get to the end of this chapter. We're going to start with a model called the Drude Model. It's named after a scientist named Paul Drude. This model dates back to 1900, so it predates quantum mechanics. And the idea behind the Drude model is pretty simple. If you've taken a Gen Chem class before and someone tried to explain metallic bonding to you the way they normally do there in maybe one slide, they probably would have said, think of a metal as an array of metal cations that have lost their valence electrons. We can treat the valence electrons as a sea surrounding this lattice of metal cations. So if we had sodium, we would have a bunch of sodium plus 1 ions, and then they would be surrounded by this sea of valence electrons. All right, so that's fine. I mean, it's very simple. It's not accurate, but it's a starting point for something. How are we going to do anything quantitative with it? Well, we have to have some idea of the behavior of those valence electrons. So in the Drude model, what we're going to do is going to treat them as an ideal gas, and then we're going to apply kinetic-molecular theory to them. So the electrons are moving very fast, but in some ways they're not really going anywhere because the electron moves fast and then it keeps colliding with the ions of the lattice. And every time it collides with one of the ions in the lattice, it redirects its path. And so over time, there's no net flow of current in one direction or the other in the absence of an external driving force. So if we're going to treat it like an ideal gas, that means we're going to use the Boltzmann or the Maxwell-Boltzmann distribution to describe the kinetic energies of the electrons. And so remember that distribution. Here I've sketched out a couple of distributions of the speed of the electron versus the number of electrons traveling at that speed. When we have a gas that's cold, we'll have a peak at a lower speed. It shifts the distribution to lower speeds and it tends to concentrate it around the average value. When the gas gets hot, the distribution spreads out, and so that shifts the maximum to faster speeds, and we get a much wider distribution. And of course, we could get this same kind of effect if we were talking about heavy atoms. That might be the blue curve, and light atoms might be the red curve. But here, what we're thinking about is the electron. What's the energy of the electron? Well, in a Boltzmann distribution, the average energy of the moving particles is 3/2 times K, the Boltzmann constant, times the absolute temperature. Okay. Well, we can calculate the root mean square velocity from this distribution, right? The kinetic energy of the particle, E, is equal to 1/2 mv squared. So if we rearrange that to solve for V, we would get the velocity of the particle is the square root of twice the energy divided by the mass. Here we're using the mass of an electron. And then if we use this expression above here for the average energy of the electrons, then we get this expression. 3 times the Boltzmann constant times the absolute temperature divided by the mass of the electron. Well, except for the temperatures, those are just fundamental constants. And so if we were to pick a specific temperature, let's say room temperature, 300 Kelvin, we could come up with an estimate of about 100,000 meters a second for how fast the electrons are moving. They're moving very, very fast because they are extremely light. Okay, that's one piece of information. Let's keep that in the back of our mind. Now, we have to define a few terms here before going any further, and that would be the mean free path and the relaxation time. So the mean free path is going to be the distance the electron travels before it collides with one of the stationary ions in the crystal. If we divide that by the velocity, then we can come up with the relaxation time, which is the length of time between collisions. We just came up on the last slide with some estimate of the velocity of the electrons, 100,000 meters per second. Well, the mean free path, I don't know. We can make a guess at this. So if you think about the structures of metals, they've got these close-packed atoms, and so things are pretty crowded in there, and you would think that the electron wouldn't travel too far before it ran into one of the ion cores. So let's make an estimate of 1 nanometer. That's maybe about 2 unit cells. Okay, that seems reasonable. If we make that estimate, then we come up with a relaxation time of 1 times 10 to the minus 14 seconds. Is that reasonable? I don't know. Seems not too far out of line to me. Okay, now let's apply an electric field and see if we can get a flow of current. Right? We want to talk about conductivity, and so if we want to get conductivity, we have to apply a driving force to get that conductivity, and that driving force is an external electric field. What we're really interested in is not so much how fast the electrons are going, but what's their net speed in the direction in which the electric field is pushing them. That we call the drift velocity. So if we start with Newton's relationship, we can say the force acting on the electron is equal to its mass times its acceleration. But the force that's acting on the electron is just the charge of the electron times the electric field intensity, small e times capital E. We can rearrange this equation, and if we do, we find that the acceleration of the electron is its charge times the electric field intensity divided by its mass. All right, now we are in a position to calculate the drift velocity, right? If we just think about very fundamental physics, we know that the velocity of an object is the acceleration times the time. And so the acceleration I've just defined up here. The time tau, right? That's the relaxation time. Okay, and so we could plug in some numbers here and come up with an estimate. And so if we take the charge of an electron, and if we take an electric field of, I don't know, 100 volts per meter, and the mass of an electron, we get something like a drift velocity of about 0.2 meters per second. Right? So that's much, much smaller than the average kinetic velocity of the electron. So it's only moving somewhat slowly in response to the electric field. And the reason why is because it keeps running into the ions. Whatever we can do to increase the relaxation time, that is, go farther without hitting an ion, that's going to increase the drift velocity, and it makes sense that that would increase the current. So let's now try to cast this drift velocity in other ways. We can talk about the electron mobility, which is represented by the symbol mu, and this is really a measure of how easily the electrons move in response to an applied field. The mobility is equal to the drift velocity divided by the electric field intensity. And it's really kind of simple. If we get a large drift velocity, the electrons respond and move quickly to a modest electric field, it means that they have a high mobility. But if we have to apply larger and larger field to get that same response, it means that the mobility is less. If we go back to the last slide, we had a relationship for the drift velocity of the electrons, and that's plugged in here. And we can see now that the electric field intensities are going to cancel. Right? This is really an intrinsic property of the material, the mobility. It doesn't really depend on the size of the electric field we're applying. And that mobility is equal to the charge of the electron divided by the mass of the electron times by the relaxation time. So if you think about it, as the relaxation time gets longer, it means that the mobility goes up. So if you want to make something highly conducting, one trick is so that when you apply an electric field, you don't want the electron to keep running into ions that are going to scatter it. Finally, at this point, we're ready to talk about the conductivity of a material in the Drude model. The current density is equal to lowercase n, and that's the concentration of valence electrons, times the charge of the electron times the drift velocity. Current density is going to be charge per unit time per cross-sectional area. And just think about the units here. The concentration of electrons is 1 over meters cubed. E is just the charge of the electron in coulombs, and then the drift velocity is meters per second. So we're going to get coulombs per second times meters squared. That is the current density. But we could rewrite the drift velocity in terms of the mobility. Drift velocity is equal to the mobility times the electric field intensity. And then to the right of the second equal sign, all I've really done is put a parenthesis around the 3 terms that come before the electric field intensity. Why did I do that? I did that because I wanted to compare with our earlier intrinsic version of Ohm's law. Right? J equals sigma times E. And so what you can see is that sigma is just equal to the concentration of charge carriers, as the mobile electrons that can respond to an external field like an electric field, times by the charge of those electrons, times by the mobility. So if we want a material to be more conducting, we either need a higher concentration of charge-carrying electrons, or we need the mobility to go up. Now let's put some numbers to this for a typical metal. So here I'm going to take sodium, which is a pretty simple metal because it just has 1 valence electron per sodium atom. And so what kinds of estimates do we get for these various parameters? Well, the conductivity at room temperature is 2.1 times 10 to the 7th. We can just measure that. The electron concentration, we could come up with an estimate of that by assuming that every sodium atom gives up 1 valence electron to carry the charge. And if you just look at the crystal structure, we can calculate that the density of sodium atoms is 2.5 times 10 to the 28th for every cubic meter. Now, knowing these two quantities, we can calculate the mobility, which we do here, 5 times 10 to the minus 3. Knowing the mobility, we can calculate the relaxation time from the mass and the charge of an electron, which I do here, 3 times 10 to the minus 14. That's not too far from our earlier estimate. And then we have our estimate of the velocity, which we took from the Boltzmann distribution. And then finally, knowing the velocity and the relaxation time, we can calculate this mean free path. And here we come up with an estimate of 3 times 10 to the minus 9 meters. It is 3 nanometers. And well, that seems pretty reasonable, right? Our initial guess at the mean free path was 1 nanometer, but who's to say that the electron might not travel 5 or 6 unit cells before it hits an ion? I mean, does that mean that the Drude model is correct? Well, not necessarily. One problem with the Drude model is it doesn't correctly predict the temperature dependence of a metal. As we'll see in the next lecture, metals become more conducting at low temperatures, which is not obvious from the Drude model because the electrons would slow down as the temperature goes down. It turns out when you make alloys, solid solutions between different metals, the conductivity goes down, and that's not obvious from the Drude model. But maybe the most damning problem with the Drude model is if we just look at how well we can use it to predict the conductivities of various elemental metals. So if we start with the alkali metals, rubidium, potassium, sodium, we can see that as the atom gets smaller, we can pack more atoms into a given volume. And so that's going to lead to a higher value of N, and that does lead to an increase in the conductivity. But then if we were to go to, say, calcium, which is divalent, then we expect the conductivity to maybe double because we have now considerably more electrons per unit volume. And it does go up a little bit, but it doesn't really double. If we were to go to magnesium, which is smaller still, and so we should have even more valence electrons, conductivity actually goes down, which is a little bit worrying. Of course, assuming that these are going to scale 1-on-1 with each other is assuming that the mobility is basically the same in every metal. And we'll see that's not true, but nothing in the Drude model gives us any idea how to predict the mobility. When we go to something like aluminum, now we have a really high concentration of valence electrons. It does have the highest conductivity in this column, but it doesn't really proportional to what we would think would be the availability or the concentration of valence electrons. And then when we go over to the transition metals, it goes all screwy. So some of them, like silver, gold, and copper, have high conductivities, even though they have only modest concentrations of valence electrons. But then when we get to things like scandium or titanium, each titanium atom having 4 valence electrons, it has a very high density of valence electrons, but yet a really low conductivity for a metal. So there's obviously something more going on than the Drude model can explain.